Hello everyone, thank you so much for attending Rack and Orbit. Thank you so much for staying all the way till the end for my talk. My name is Ganesh and today we'll be talking about scale. So TypeDB is a database system that exposes an expressive, powerful, and strict query language. Application developers can leverage TypeDB and the expressive query language to build an intelligent application. Over the past year, we've sort of revamped TypeDB all the way from the top down to the bottom, down to the storage layer. And for all of you that is interested in knowing what's the approach that we take as well as the philosophy behind it, feel free to go and check Heikel's keynote on Orbit. As for now, though, what we're going to talk about is something a bit different. So we know that TypeDB is a database that allows you to model complexity. So what do we want to do with it? Well, first of all, we want to make sure that our user is able to not only express their complex problem, but also does so in a way that scales. We want our users to be able to use TypeDB at the front line, serving their mission-critical systems. Therefore, with this that serves as the primary motivation, we're pleased to announce our new flagship product that will sit side by side alongside TypeDB. This product is not only meant to solve complexity, but does so at scale. We call this product the TypeDB Cluster. TypeDB Cluster is fully compatible with TypeDB, and application developer can switch from TypeDB to TypeDB Cluster without any modification. It is completely highly available and scalable, and does so with the use of clustering. This key functionality is supported by one of the key components, which is something that we've built, which is our own homegrown distributed storage engine that is efficient and robust. And we're going to see how this thing works under the hood in a bit. So it is scalable, and it does so by leveraging the fact that there are multiple TypeDB instances that works together as one. Applications can distribute the queries across the servers, allowing for maximum throughput. And should some of the instances fail, the application will be able to failover between the failed instance and onto the functioning instance transparently without any user intervention. Now, this system has been used in production by some organizations, one of which is actually us. And this is something that we haven't really have time to talk about. But we've gone and go to create our own CI/CD platform that we use throughout the organizations. And if you go to one of our repo, you'll be able to see that the tests are actually run on this particular platform, which is now what we call the Fatical Factory. So Fatical Factory has powered our workflow and makes us way more productive in the past couple of years. And since about 4 months ago, at the launch of Kraken 2.0, well, it used to be called Kraken 2.0, right? At that point, we switched it over to the cluster version, which is now called TypeDB Cluster, and it's been running fine since. So now let's learn more about the functionality of TypeDB Cluster and how you, as an application developer, can leverage its high availability as well as scalability functionality. Now we're going to take this diagram and we're going to make it a bit simpler. Let's only have like one application with 3 servers, make some room for more components that we're going to show under the hood. Let's also make it a bit bigger. And Let's consider a very typical deployment of a single application running with, say, a cluster with 3 servers. Let's say this is, like your typical e-commerce application or your food delivery application, right? So this application, say, works with 2 databases, database 1 and database 2, shortened as DB1 and DB2 in the slides, right? Now DB1 and DB2 each has separate copies on each of the server. This individual copy is what we refer to as the replica. Therefore, DB1 and DB2 each have 3 replicas sitting on each server. Now, each replica may play a specific role. One replica may be designated the primary replica, whereas the rest of the replica will be designated as the secondary. In the case of DB1, the primary replica sits on server 1 on the left, whereas for DB2, the primary replica sits on server 3. Now, as a like typical application, obviously wants to perform some reading and write some data as well, right? Like it needs to do some insert query, it needs to do some match queries, right? And how do we serve these kinds of queries? Well, queries are typically handled by the primary replica. So in the case of wanting to write some data, let's say some user transaction data into DB1, the application will have to talk to the primary replica of DB1, which sits on server 1. Now, obviously, all of this is something that is handled transparently, and you don't need to code the logic of selecting the right server, and instead, these are handled by our client. Now, say the application needs to talk to the other database. It needs to talk to DB2 to insert different kinds of data. Say DB1 is more for user transaction, and DB2 is more for, say, let's say, like some particular kind of analysis that pertains to the user, right? Let's say the analysis of their activities and whatnot. So what's interesting to see here is the fact that the primary for DB2 sits on a different server than DB1. And this has allowed us to scale writes such that the load may be handled between different servers. In this case, server 1 and server 3 are both handling the writes for different databases, allowing for some degree of fairness between the server and the cluster, such that not everything has to be done on a single server. So this is in contrast with some other like simpler model of database where one server is designated as the primary server, whereas in our model, the primary replica may sit on different servers for different databases. So it does allow us to be a bit more scalable to some degree, right? And the operations that you do here in terms of read and write are something that is commonly referred to as a strongly consistent operation. So a strongly consistent operation means that the operations that you do always sees the latest data. So if you've recently insert some data and then you want to read from the database, you will immediately be able to see that data. Now let's say that server 1 fails for whatever reason, right? Say it runs out of RAM or runs out of disk space, right? It goes down. Now the primary replica of DB1 was sitting on the first server. So what's going to happen? Well, what will happen is an automatic failover process will take over, and the servers will somehow be able to decide that they need to designate another replica to act as the primary replica, given the fact that the original primary replica is now unavailable. So the primary replica of DB1 may be designated to the replica that sits on server 2 or 3, Both are possible. And in this example, let's say that it falls under the jurisdiction of server 2. The application will eventually be able to transition in a transparent way from connecting to DB1 in server 1 to connecting to DB1 in server 2. Now we've touched a little bit about how the read and write operations are made more scalable by the introduction of this design, where each database has its own primary replica, which may sit on different servers if you have more than one databases, right? But what if you want more? What if you need it to be more scalable? What if, for example, you want the load to be distributed completely evenly across the servers, right? Let's say you want to run some really, really heavy query that takes up so much computing power from a single server. So therefore, it's obviously quite intuitive for us to want to be able to scale out and have more instances in order to serve the throughput as needed by the applications. And for this particular requirement, we decided to add a new mode that is specific to ReadAny Cluster, which is the ReadAny Replica mode. In ReadAny Replica, the read operation will be able to be load balanced across the servers in an even way. Therefore, the implication is if you have 3 servers, you'll be able to enjoy a 3x throughput increase. Similarly, if you decide to increase the number of replicas even more, to have say 7, right, you will enjoy practically 7x increase in terms of the read throughput. So what's the difference between ReadAny Replica and a regular read? When do you use read and when do you use ReadAny Replica? Well, the answer to that is ReadAny Replica, unlike read, do not guarantee strong consistent view of the data. And what that means is it is possible for ReadAny Replica to return not the most up-to-date version of the data. And therefore, ReadAny Replica should be used when your application can tolerate some form of staleness in the data. So for example, if you want to display the latest balance in a user's bank account, you would probably want to stick with the regular read. Whereas if you want to compute something that is less sensitive, say for example, what's the average of product that we sold last month, right, on average, then you might want to use the ReadAny Replica instead. Now that we've covered the basically the main functionalities of ReadAny Cluster and how you can leverage TypeDB Cluster for operations that needs to be performant and also highly available, let's try to go down a bit more, get a bit deeper, and try to understand how things works under the hood. So let's start with a question of how does a client even know to talk to which server? So let's say that we're going to zoom in a little bit into the application. Say the application obviously needs to embed a TypeDB client in order to be able to talk to the cluster, right? Now the application needs to decide somehow between these 3 servers which one to connect, right? Based on some criteria. The first step to connecting to a cluster is what we term as the handshake. An application does not need to initially know about the existence of the servers in the cluster. Sorry, that's not really right. What I'm trying to say is the application doesn't need to know about the existence of each and every server that exists in the cluster, but instead it only needs to know a few. So it doesn't really matter which server it knows, as long as it is a server that is currently available in the cluster. And what it's gonna do is it's gonna try to contact any of the server, right? And it's going to receive back a reply from the server with full information about the member of the cluster at that point, as well as the information about the database that the client is interested in. For example, if the client needs to be able to perform operations on database 1, then it'll receive information about where is the primary replica for database 1. For example, the primary replica for database 1 in this case is on server 1. And similarly, it's going to receive an information about the fact that the primary replica for DB2 sits on the third server. So aimed with this information, the client now has the ability to decide on where to connect depending on the operations. If it wants to do an operation, an insert operation to DB1, then it knows that it needs to talk to the first server. Whereas if it only needs to do a ReadAny replica for either DB1 or DB2, then it knows that using the full information about the cluster servers, it'll be able to talk to any of them. So now we've taken a look into how the client can mediate connections with the cluster. We're gonna change the diagram a little bit, make more room, make the DB1 primary a bit bigger, because the next question that we're gonna answer is something that's quite crucial, is how does your data get distributed across all servers? You perform a write that gets into the primary replica, which sits on server 1. And server 1 now has a responsibility as the primary replica to replicate the data across all servers. Now, in a distributed systems, we need to start with the right assumptions. So, for example, we need to be able to assume, right, that the CPUs should be reliable. It should be able to perform the right computation where 2 plus 2 equals to 4. We should only assume that we can trust the disk, that if we write the data to the disk, it will be stored in a way that's not corrupted and in a way that's persistent and can be retrieved later, right? So we need to start with these two assumptions. However, there are some other assumptions that we shouldn't make, right? Which is, we shouldn't assume that the machines are always on, because that's not the right assumptions to make, because machines die all the time, right? It may run out of RAM, it may run out of disk, and it may die due to various other reasons. Similarly, we can't assume that the network is reliable. When you're trying to send some data over the network, several things might occur, right? Most of the time, it gets sent, right, in the right way, but some other time, it may either be lost, or it may be duplicated. You do an insert, and on the other side, it receives insert. Or, what's even worse is if they start reordering the messages, right? You do insert delete, but it is received as delete insert. Now, these things can cause problems. Imagine if we don't take these things into account, what's going to happen is the replicas may go out of sync, because the operation that is done in one way on the primary replica may be received in different order on the other replicas. And therefore, the replicas go out of sync, and therefore, it's not really good. So let's make some room and try to understand what's the solution based on that assumptions. So, introducing the replicator module, which acts as the key component in TypeDB Cluster that allows data replication to happen in a safe and performant way. Replicator is based on sound principles and algorithms, namely the RAF protocol, as well as the actor model as the key algorithms. And they're also built using a proven technologies such as RocksDB for data storage, as well as 0MQ for networking. So the replicator is based on raft, and therefore let's take a look at the key ideas behind the algorithm. So each replica that is stored in a server is associated with one instance of the replicator. Each replicator instance plays a role, which is either a leader or a follower. And here I'm quoting the actual raft terminology on the paper itself. It can either be a leader or a follower. Raft guarantees that there's always one and exactly one active leader. The data flows one way from the leader to the follower. And all of these are achieved by means of several protocols working together, namely the leader election protocol and the replication protocol. So let's take a look at the first key element here, which is the leader election protocol. And this is the protocol that guarantees that there's always exactly one active leader at any given point in time, regardless of any failures that may happen in the system, right? So every replicator instance starts as a follower. A follower will try to listen for a signal from the leader. Each follower has a specific timeout setting, which is what is called as the election timeout, which is randomized between some value to some other values, which in this case results in, say, an election timeout for 500 milliseconds, 300 milliseconds, and 700 milliseconds between replicator instance 1, 2, and 3 respectively, right? And this election timeout will be triggered if it doesn't hear from any leader for that period of time. When the election timeout has been reached, an election is triggered, and an instance always proposed itself to be the leader. So we can consider each instance to be selfish, that if it doesn't hear for any leader, it's going to try to propose itself to be the leader. A single election run is identified by its term number. The term number is unique and allows each leadership period to be identified. An instance never votes more than one for a given term. And what that means is, if, say, server 2 starts an election with ID 1, should server 3 start an election with also ID 1, server 1 will never vote for both server 2 and server 3, but rather will only vote for one server, either server 2 or server 3. An instance will become the leader if it receives votes from the majority of the servers, which includes itself. So in this case, for any of the server to win, it only needs to receive one vote from its peer, given that it already votes for itself. The timeout values are randomized for a specific reason, which is to try to minimize. And I say minimize, meaning that we don't try to prevent it completely because it's impossible. We just try to minimize the occurrences of multiple elections happening at the same time. Having multiple elections happening at the same time is not dangerous, and it doesn't pose any threat to data safety, but it does cause some performance issues because it'll be more likely for the election to not reach a consensus of who should be the leader, because maybe half of the server will vote for server 1 and the other half will vote for server 5, for example, right? And when that happens, the election will need to be re-triggered. Therefore, we should always try to minimize the number of elections that happens concurrently. Now that we understand the basic principles of how leader election works, and this is by no means a complete list, right? But with this intuition, let's try to play out the election. Given that server 2 has the shortest election timeout, it is very likely that server 2 will be the first one that initiates an election. So say server 2 initiates the election, and it'll change the role from what is from follower to what is known as the candidate in Raft's term. As it becomes a candidate, it increments the term number from 0 to 1, right? And it informs the first instance and the third instance of the replicator about the election. Now, as soon as server 2 receives a response from either server 1 or server 3, consensus is reached, because that means 2 out of 3 instances have voted for server 2. Sorry, for instance 2. At which point, the server 2 becomes the leader for term 1. As soon as an instance becomes the leader, it'll inform the other instances of its leadership. And in this case, the first and the third instance are now aware of the fact that server 2 is the leader. The key takeaway here, though, is that the election can already be decided by the participation of the majority rather than all server, which means that should any of the server becomes unavailable, the algorithm can still function. And this is a key feature of the algorithm that allows the system to be highly available, because you can still progress while having one server out of the 3 server unavailable. If you have more servers, you can tolerate more failures. If you have 7 servers, you can tolerate up to 3 servers, given that you still have 4 other servers, which consists of which makes up the majority out of the 7 servers. So the ideas are quite simple. What's interesting about it is the fact that it always works. I'm not going to go deep into how it works under the hood, but the intuition is there. And what's important is this algorithm works regardless of timing and regardless of arbitrary failures that may happen during the course of the run. Therefore, the leader election process is a robust process that we can rely on. And in fact, we're going to use this leader election step as a key building block for the most important part of the replicator functionality, which is the log replication. Therefore, let's make some room for the components, because we're going to introduce a few more key components within the replicator, right? So basically, in the replication, the data always flows from one way, from the leader to the follower. And the data is only committed once the data has been safely replicated. Again, not to all servers, but rather only to the majority of the servers, to the 2 out of the 3 servers, or to the 4 out of the 7 servers, for example. Which means that the replication algorithm is also highly available and can tolerate some degree of failures. So the 2 key components that we're going to introduce here are, first, the log, or what we call the replication log, right? And the other one being the data storage. So basically, the replication log is a persistent store that allows you to keep track of the ongoing replication. Whereas the data storage is the final place where the data will sit once the replication has finished. So when a user performs a query, say it wants to insert a new person with a name Bob, right? What's going to happen is that this query will not be immediately inserted into the database, into the replica, but rather it will have to be first put in the log to be prepared for replication. Once it's put in the log, in the leader, it's going to be replicated to instance 1 and to instance 3. And as soon as it receives a reply from one of the server, 2 out of the 3 servers have stored the data, and therefore it's enough for the algorithm to proceed. At which point the data will be safely stored in the storage. So although I say that the algorithm will manage to proceed after replicating to the majority of the server, it must eventually attempt to make sure that the data is finally replicated to all servers. And while the algorithm proceeds to to serve more queries, the replication for the instances that are left behind will continue to happen in the background. So for example, if you're performing an insert followed by another insert, say the first insert did not go to the server 3 because server 3 went down. However, the data can still be committed given that it's replicated to server 1 and server 2, and it can continue to process the next insert, right? However, in the background, server 3 will continue receiving the information about the first insert. So basically, the leader will keep on retrying the insert for insert number 1 indefinitely to the third server, while at the same time, obviously, receives and processes ongoing requests, incoming requests from the user. Eventually, the expectation is for server 3 to go up. And once the server 3 goes up, it's going to try to basically keep up with the data that it missed, right? Oh, I missed query 1, I missed query 2, I missed query 3. Let's synchronize them all the way, which may take some time, but eventually it'll be able to receive all data points. So at some point, we can expect that all data will be stored in the data store in a way that's completely identical between one replica to another. And this can happen in a way that's deterministic, even in the face of failure that may happen in the machine or the network. So essentially, the replication log is a very key element here. It's a very important component that basically stores the information about how to reproduce a given state on a replica in such a way that the end result will be the same between one replica to another. So the summary of these protocols, both leader election and log replication, is the fact that Raft allows you to perform a safe and robust data replication despite the weak assumption that we can make regarding the reliability of the systems, in which case the machines and the network. And what's cool about it is all of these are done in a loosely way, right? In a loosely coordinated way. There is no global atomic locks. There is no global synchronization. And the fact that there is no global view that one instance may have regarding the other instances, and all instances works within their own limited views about the whole system. For example, if a leader dies, obviously it may take some time before a follower knows that the leader has died, right? It doesn't immediately know, because the only way it'll know that the leader dies is if it hasn't heard from the leader for some time, for example. So it's really cool that essentially this is an algorithm that works in a way that doesn't leverage any full information about the state of the whole system. So now that we've understood the key principles of the algorithm, the question is, how do you implement it? So this is what we it's the goal is very simple, right? The goal is you want to get the data to be identical from one machine to another. It's essentially like, how do I copy the data over from one side to another? So therefore, it's ironic in a way that the goal is very simple, but actually the challenge in achieving that in a way that's reliable is incredibly hard. Well, not incredibly hard, but it's somewhat hard, right? So the problem is inherently event-driven, inherently concurrent, inherently faulty, and they need to be modeled. They need to be modeled in the implementation so that we don't lose clarity of what we need to do, right? You have the model, and you need to make sure that your implementation adheres to that model in order to not lose clarity. So we've looked at several approaches on how to model this problem, and we found out that the actor model is one that provides you to encode distributed systems behavior in a natural way. So I don't know how familiar you guys are with actor models, but essentially, unfortunately, I won't be talking too deep into the actor model. However, what's important is that in actor models, you model the problem as a set of actors where one talks with another. The communication within one actor to another happens asynchronously by the use of message passing. And each actor stores their own state, and no actor can have access to the state of another actor. It's all shared. It's all based on the shared nothing approach. Share nothing, message based. And what's cool about the actor model is that what's hard to do in distributed systems is actually hard to do with an actor, such as sharing global state and performing global coordination between actors are hard, and therefore you are naturally discouraged to do so, which lends yourself to be modeling the problem in a way that fits with the reality. So the problem, you are encouraged to design the algorithm in a way that is naturally event-driven and non-blocking, where messages are sent in an asynchronous way. So what resulted is an implementation which is completely lock-free. We don't have any locks in our rough implementation. It's completely event-driven. It has many benefits, one of which is the event-driven and non-blocking communication model. So let's take a look at this diagram where we have the communication between the leader and the follower. So the leader is trying to send 3 messages to the follower. On a classic model, what's going to happen is that the leader will send a message and wait for a response from the follower in order for the leader to continue sending the next message. That will be probably quite a default programming model that people would typically do unless they start doing optimization and realizing that these are things that we can do. But what's cool about Actor is these things are just natural, and this is just the way you work with Actor. So the design that we go for is, for example, it allows the leader to communicate with the follower, sending one message after another, and only receiving the response later on. For example, in this case, you can see that the purple request, which is the first request that is made by the leader, is then immediately followed by the second request, which is the red request, and the third request, which is the green request, without even waiting for the follower's response. And what's cool about it is obviously there needs obviously you need to recover from a condition where if, say, the follower says that the first request is rejected, that you need to basically follow up with that, right? But what's cool about it is you immediately think of solving the problem in this way, in an event-driven way. Try to be optimistic, send 1, send 2, send 3, and if the response for send 1 fails, then maybe you need to resend 1 again, right? But you start off by being optimistic, by taking into account that communications are non-blocking, and therefore treating event-driven and non-blocking design as a first-class citizen. So the actor model is an established concurrency model that's been around for a while. It's been used in different organizations and products, right? We have our own homegrown implementation, which is quite cool. This is something that originated from TypeDB Cluster. We've been familiar with the model for a while, but on TypeDB Cluster, we decided that we need our own implementation to fit our need. It is currently used extensively across different code bases, which includes the reasoner. And stay tuned for Joshua's talk, because he's going to cover actor model in a more complete way on his talk, right? Unfortunately, I can't cover that due to time. So that's the actor model. We've managed to model the problem in a more natural way, given the fact that it's concurrent. So what other things can we take? What other steps can we take in order to make the problem looks even more natural? How do we capture the problem more? The other thing that we notice is that we have to implement different kinds of transitions, and we need to operate in different modes depending on the current state of the systems. Therefore, we think it's the right time to use the concept of finite state machine. So we take the textbook's concepts of finite state machine and try to model our problem of replication in this model, where, for example, if you're on a state leader, what do you do? Versus if you're on a state follower, what do you do when you receive the same kind of message, right? If you receive a request for election, you need to behave differently when you're a leader versus when you're a follower, for example. So the encoding of this algorithm using a finite state machine allows us to reduce complexity by encoding transitions in a type-safe way that closely model the problem and also eliminate or at least minimize invalid state transitions that you shouldn't do. It's made impossible, or at least very hard to do, because you'll immediately notice that you're trying to do state transitions that is, according to the protocol, something that you shouldn't do, right? So modeling them in the right model allows you to easily spot these kinds of problems. So we've taken a look into how we decided to go with our implementation. Like, what kind of model do we go for? The problem itself is still inherently quite complex, right? And we need to guarantee our correctness. Therefore, we've taken the concept and implemented it in a way that's we think is as simple as it can be. Now, the next thing that we need to do is we still need to somehow verify whether implementation is correct. At least we know the model is correct. At least we know that the IDS is correct. But how do we ensure that the implementation is correct? And what we did is we introduced another key implementation to the whole thing, which is the ability to verify that the most complex bit of the implementation, which is the replicator component, can be tested in a way that is fast. You want to be able to receive fast feedback if there is an error, and you want to continue iterating on the implementation in a very productive way, right? With a very fast turnaround, right? And the solution for that is basically the way to run the instances in a simulated environment, which is deterministic. So we've built our own deterministic simulation framework that allows you to run multiple rough instances, replicator instances, making sure that all the non-deterministic components are swapped out with a simulated deterministic one. For example, we replace a network layer with a deterministic network layer, which allows you to model and simulate different kinds of failure in a deterministic way, as well as replacing the clock that is used in several components in the implementation, such as for performing leader election and sending heartbeat, with a deterministic one. So what results from this is a very productive framework for us to model and to run the test in a way that is completely reproducible. If we start off with some configuration and we see that on iteration 705, the test would fail due to null pointer exception, we can simply rerun the test again, rerun the simulation again, and it'll fail at exactly iteration 705. In order for you to explore more combinations, more permutations, all you need to do is you would change the randomizer seed, and it'll try different kinds of permutations to expose more failures. And basically, this mode of iterating, of just running the test, making sure they pass, and then changing the configuration, making sure they still pass, has been key to the speed of development of TypeDB Cluster. So to wrap up the talk, basically we've presented you a new flagship product of Vertical, which we call the TypeDB Cluster, which is a highly scalable, highly available database for production that should serve clients on the front line for their mission-critical systems. And that TypeDB Cluster is essentially built on 3 key pillars, which is clustering with the use of an event-driven and non-blocking implementation of RAF that we do, concurrency, which is done with our own implementation of the actor model, and the verification, which is done using our deterministic simulation. And basically, that's basically our philosophy, right? We first look at so we've looked at the right assumptions for building a distributed systems on what can we trust and what we cannot trust. For example, we can't trust reliability of machine and network, and from that assumptions, we start looking into what is the best algorithm that can serve our purpose, and then we go on to how do we best model the implementation in terms of the concurrency and a computation model that captures the problem, and then we go on to how do we verify them and ensure that they work in the best way possible in a way that's productive. So that would conclude my talk on TypeDB Cluster. We're really excited about the product. We've seen it being used by several organizations, and we hope that we'll see more. This software is available to be deployed on different cloud services. It can run on Kubernetes, and in fact, we have Helm package that can help you run the software on Kubernetes. So we have some questions. I'm going to come back in a bit. I'm going to read up these questions. So the first question is from Christoph, and the question is, so if we read from any replica, we will lose consistency. Right, so I suppose you're referring to the ReadAny Replica feature, and whether we're going to lose consistency if we read from the using the ReadAny Replica. And the short answer is yes, you will lose consistency, and therefore essentially this is a trade-off between consistency and reliability. Therefore, if you need to make sure they're consistent, you do have to use the read operation rather than the ReadAny Replica operations. However, there are efforts that we're making in order to improve the consistency a bit more. We're thinking of implementing the read your wide consistency model, which we haven't, and we may support quorum reads in the future to allow for scaling reads in a way that is still fully consistent. And the next question is, why did you decide to implement your own replication framework rather than using a framework that's already there, such as, what is this, Chef? I've never heard of this one, Chef. Well, okay, so I think essentially the question is about why do you have to implement your own replication algorithm? Well, the answer to that is we've actually done some research and regarding a possible approach of using an existing libraries, but the answer is that we want to have full control over the algorithm itself. So we prefer to build our own, given that we want to optimize it in the way that we use it exactly the way it is. So we have a very strong type system, for example, and we actually want to leverage these informations to perform replications in a way that suits our needs in the most efficient way possible in the future. And therefore, it can't just be any generic replication algorithm. Okay, I think that's it. Thank you so much. These were good questions. Thank you so much. Thank you for attending my talk. Obviously, there will be more innovations coming in TypeDB Cluster, and yeah, you guys should stay tuned. Thank you so much. I'm signing out. Thank you so much. Bye.